Today's session we start with example on Darlington emitter follower, followed with transistors at high frequencies, and also we will discuss the transistor parameters at high frequency and relating to the transistors at low frequency, and later we will derive an expression for the voltage gain of a transistor at high frequencies. Darlington emitter follower uses identical transistors and calculate voltage gain, current gain, input resistance and output resistance using approximate hybrid model with data Rb equal to 2.2 mega ohms and Re equal to 1.2 kilo ohms, and assume H parameters. For the analysis of this transistor amplifier emitter follower, we need to derive an expression for the input impedance, output impedance, voltage gain, current gain of an amplifier. Means where input impedance is defined, means you are looking into the terminal Zi, and output is to be taken across, output impedance to be looking into the at this point Z0. Okay. And also we need to derive an voltage gain AB equal to V0 by Vi, and current gain AI equal to AI0 by II. For this derivation, we need to replace the transistors with its equivalent value. Then that hybrid model means this is the first stage input resistance HIE, and then this is on HFE times IB1. Current flowing through this is IB1, base, collector and a emitter. The second transistor is cascaded directly from emitter of this is connecting to the a base of the secondary, then it is connecting to the HIE identical transistor, and then this current flowing through this is nothing but is an IB2. Then this current is to be IB2 times HFE, and then the resistance is connecting across this point RE. To transferring that collector, both a C1 and C2 are directly connected, hence this two are directly connecting to the VCC because your set VCC is grounded. And then when you are looking into this point, that base resistance RB is connecting between that a base and a ground. For this we need to determine that input impedance means you are looking into this point ZB, and then we are looking into this is Zi. We are applying ZB to find an input impedance. We need to find that ZB is equal to VB or Vi by IB1. The current flowing through this is IB1, current flowing through this is IB2, and current flowing through this is your IE. When you are looking into the voltage at this point is Vi. Therefore, input impedance ZB is given by Vi by IB1. Means here IB1 means you have to derive an expression, means applying KVL to this path excluding that resistance RB. For this case you are going to get a ZB, means applying KVL to this means you are going to get Vi minus HIE IB1 plus HIE IB2 plus RE into IE, where that IB2 is equal to IBE1, this is equal to 1 plus HFE times IB1, and IE is equal to 1 plus HFE times IB2, hence this is equal to 1 plus HFE square IB1. If you substitute into the above expression, we are going to get Vi is equal to HIE plus HIE into 1 plus HFE plus 1 plus HFE whole square into Re multiplied with a base current IB1. then Vi by Ib1 is equal to Zb is equal to Vi by Ib1, this is equal to HIE plus HIE into 1 plus HFE plus 1 plus HFE square into RE. The problem statement is we need to calculate an input impedance. You have to substitute the values of HIE and HFE and RE value. Where we know that already assume means we are given assumption means you have to assuming that HIE is 1.1 kilo ohm and HFE is 50. If you substituting these values, then your input impedance is 1.1 into 10 to the power of 3 plus 1.1 into 10 to the power of 3 into 51 plus 51 square into 1.2 into 10 to the power of 3. If you substitute and add, you are going to get this value is equal to 3.178 mega ohms. For this case, if the HIE into HIE plus this, when compared to that HFE is 50, then this square is approximately equal to 2601. This value is much greater than that 1 plus HFE, and then this term is much greater than HIE. Then ZB is approximately equal to a 1 plus HFE whole square times RE. This value is approximately equal to 3.1773. Means this value when this HIE plus into 1 plus HFE plus this value is approximately, even if you are neglecting this value, that input impedance is to be slight because only in the fourth decimal point it changes. Therefore, that approximate input impedance is given by this HIE into this. Similarly, we need to calculate output impedance when you are looking into this point. When looking into the output impedance Z0 means output impedance Z0, you have to set Vi is equal to 0. When Vi is equal to 0, this is acting as a short circuit. When this point is acting as a short circuit, then this is, when you are looking into this point, this terminal is to be looks like HIE and one more HIE, this is 1 plus HFE times HIE, and then this is RE. When you are looking into this is acting as a short circuit, you are looking into the point this RE, Z0, where Z0 is given by, means these two are in parallel. Hence, we can say that output impedance from this circuit Z0 is equal to RE is in parallel with approximately equal to HIE into 1 plus HFE. This value, if you substitute this output impedance Z0 is given by this RE, approximate this value is to be approximately equal to RE 1.2, sorry, RE is in parallel with HIE. This value is less than that around 500 ohms. And similarly, voltage gain of an amplifier is given by voltage gain AB. Next is we need to determine an voltage gain. This AB is given by V0 by Vi, where V0 is nothing but a voltage drop appears across this terminal. Therefore, from this circuit V0 is equal to 1 IE times RE. This IE is nothing but 1 plus HFE square into IB1 into RE, and Vi is given by, from this expression, this is nothing but ZB into IB1. If you take this ratio, then AB is given by 1 plus HFE whole square RE divided by this ZB value, where ZB is given by an expression that is a HIE plus HIE into 1 plus HFE plus 1 plus HFE whole square into RE. Therefore, already we know that this value, this is 2601 or 51 square into 1.2 into 10 to the power of 3 divided by 3.1778 mega ohms or into 10 to the power of 6. This value is approximately equal to 0.98. If you observe in this case, output in a Darlington emitter follower, input impedance is increases from that HIE to a 1.1 kilo ohms to 3.178 mega ohms, and then voltage gain is to be approximately equal to that 0.9. It is approximately close to that one only. Next we need to determine on current gain. Already we know that a current gain of an amplifier is given by I naught by II, where AI is equal to that current is output current is IE and input current is IB1, where IE is equal to 1 plus HFE square into IB1 divided by IB1. This is approximately equal to 1 plus HFE square. Means here the current gain of an amplifier is increased by that factor 51 square. Therefore, this is equal to 51 square. This is approximately equal to 2601. Okay. This is the one example on Darlington emitter follower. If you are observing this with respect to the emitter follower, that input impedance is greatly increases, current gain is also greatly increases, that output impedance is greatly reduced, and then a voltage gain is remains same, is approximately equal to 1. Next, let us consider a transistors at high frequencies. Because we know that if you consider the response of an amplifier, frequency response of an amplifier, it remains constant and decreases. This decrease in gain, why? That question arises. In the earlier case, that gain is increased, and then at mid frequency gain is constant. At high frequencies, that gain is reduces. Can you justify why it is reduced? This a reduction in a gain at high frequencies, that is due to the internal capacitance of a transistor. Means this implies that if you consider this is a transistor model, then if you have two junctions, that these two junctions are acting as a parallel plate of a capacitance, then this junction capacitance is denoted with CE. This is emitter base, and then this junction is acting another parallel capacitance. This junction is to be denoted with CC. It is because B is common for both the collector and the emitter. From this equivalent circuit, if you write an equivalent symbol of a transistor, emitter and a collector and a base, there is a resistance existing, capacitance existing between CC, and then there is a capacitance existing between this C. These capacitances are greatly influence at the high frequencies, and then this gain of the amplifier decreases as the frequency increases. Hence, we need to study that transistors at high frequencies. The transistors at high frequency is transistors at high frequency model. This hybrid model is also known as a pi model. It is also known as geo-collector model. Here we have to consider the resistance and the capacitors. If you observe, we have to, instead of a base B, we are considering that B dash and B, where B dash is not physically accessible because the doping concentration at the B base is lightly doped, and then you have to use the conductor. Therefore, you have to connecting that B dash, where you have to defining that so many parameters. There is a between B dash and a emitter, that resistance, because of this conductivity, some resistance is existing. That resistance is to be defined as R B dash E, and between the collector and a base, we are shown in this figure that as a capacitance is existing, and then that this reverse biased junction is to be replaced with its equivalent resistance and a capacitor, that is given by CC and RB dash C, and there is a between the base B dash and a emitter, there is a resistance capacitor CE, and the output circuit, this is driven by the voltage source, then that constant current source is given by Gm into V B dash E, and there is a resistance. Even there is no junction between the emitter and a collector, but due to the its transfers from a low resistance path to the high So means this is a some forward bias to the reverse biased conditions. Due to that, there is a resistance is existing. That resistance is known as an RCE. Then output taken across the collector and emitter is denoted with an VCE, and between the emitter base emitter junction voltage is denoted with VB dash E. Now we define what is this RBB dash, RB dash, RB dash C and RCE CC. Already we know that RBB RBB dash is the base spreading resistance. This is due to the conductivity between the external lead and the base of a transistor. And then RB dash E is defined as a resistance lies in between a base and a emitter, and it is also denoted with that instead of a resistance normally we will measure in terms of a conductance. This is also equal to GB dash E, where GB dash E is nothing but the conductance between the base and a emitter. And similarly that RB dash C is defined as that a conductivity means a resistance between the base and a collector, that is due to the reverse biased junction, and CC is the capacitance base between the base and a collector, and RCE is the resistance between the collector and a emitter, and it is denoted with a conductance that is given by GCE, and similarly for RB dash is denoted with GB dash C, reciprocal of that, where VB dash E is the voltage drop across the emitter and a base, that is shown in that figure. These are the some important parameters of the transistor at high frequency, where CC is to be a reverse biased. Therefore, this is also known as a transition capacitance between the base and a collector, and then CE is the emitter base junction is forward biased, and then the CE is to be defined as a capacitance between the base and a emitter. This the capacitance is also known as a diffusion capacitance of a transistor. These are the some definitions of this transistor parameters at high frequency models. Now next question is, what are the values, some approximate values or ideal values of a transistor? How do you define? This transistor parameters are given by based on that a transistor diode model. We know that already this base emitter junction is forward biased, hence that B dash E is approximately equal to 1 kilo ohm resistance, and RCE and RB dash is nothing but a resistance between the base and a collector. It is a reverse biased. Therefore, this RB dash C is approximately equal to some about a 4 mega ohm resistance, where RBB dash is the a conduction, a base spreading resistance. It is a leads the external lead connections is a good conductor, hence this value RB dash B equal to about 100 ohms. Next, RCE is the resistance between the collector and emitter. Even there is no junction at this emitter and a collector, because it transfer from a low resistance path to the high resistance path. Hence, because of the transfer of a resistance from a low to high, this is normally this value is a geometric mean of that reverse biased and emitter base. This is about 80 kilo ohm resistance. And then other two parameters are CC, CE and GM, where CC is the stray capacitance. It is when the diode is reverse biased. This value is about a 3 picofarad, very low resistance value, capacitance value, and CE is the diffusion capacitance between the base and the emitter. This value is approximately equal to 100 PF. The GM is the trans conductance means it transfer a voltage into the current, hence this is known as a trans conductance and denoted with GM. This value is equal to 50 milliamperes per volt. These are the some ideal values of a transistors at high frequencies. Next, we have to find what is the relation when this transistor model is to be a pi model is to be approximated at low frequencies. What is the effect on that? We know that already this transistor at low frequencies, this capacitance CC and CE are acting as a short circuit. Therefore, normally it is that reactance at low frequency, that reactance is very high, therefore it is acting as a open circuit. Hence, in the hybrid model means transistors at pi model at low frequency is approximate, means you have to removing that a capacitance, because these two are CC and CE are approximated, are open circuited. Hence, that a transistor pi model at high frequency as shown in that figure is removing that a capacitances. And the second figure shows this is the hybrid parameters at a low frequencies. Now, we need to find that relationship between that hybrid parameters of a transistor and a pi model and a H parameters. These are related by how these two are related. Next question, because whatever the circuit we are written here, this circuit is a equivalent model of a pi model at low frequencies. Now, we can be able to relate. We know that to relating that, first thing is you have to find a transconductance GM. To determine the transconductance relationship with GM, where GM is nothing but a change in the current to change in the voltage. As transconductance means with respect to the output current with respect to the input voltage. Therefore, this can be defined as delta IC divided by delta V B dash E. Okay. For this current relation, we need to find that derivation. We know that what is IC? IC is given by a alpha times minus alpha times IE plus ICO, where IE is the emitter current, alpha is the ratio of charge carriers at the collector to the charge carriers at the emitter, and ICO is the reverse saturation current. If this reverse saturation current is negligibly small when compared to IE, then this IC is approximately equal to minus alpha times IE. This also alpha is close to 1, because that a base emitter junction is lightly doped, there is no recombination current is to be negligibly small when compared to that IC and IE. Hence, this IC is approximately IE, where negative sign is indicating that if the input current, both the currents are leaving that node, therefore, this current is negative. Then, if you consider the magnitude of IC is approximately equal to a magnitude of that emitter current IE. Now, if you are differentiating this IC with respect to that, we got this value. We know that already that input resistance RE, because when this diode is forward biased, then that RE is given by VT divided by IE, emitter current. This emitter absolute value, this is nothing but a VT divided by magnitude of IC, because there is negative sign is there, you have to remove that negative sign. The resistance value is always positive, this negative sign is indicating the flow of a current. Hence, if you are comparing with respect to this, then GM is nothing but 1 by RE, this is equal directly proportional to IC and inversely proportional to VT. Hence, we can say that where VT is at room temperature, VT is equal to 26 millivolts, then a GM is given by GM is given by a IC magnitude by 26 millivolts. It is approximately equal to GM is inversely proportional to the resistance RE. This is the one relationship between that a transconductance of a transistor at low frequency and high frequency. Next point is, then what is the relation between the input resistance R B dash E and the input resistance HIE. Now, we need to find that in a relationship between the input conductance or the input resistance that is given by R B dash E, or we can also find 1 by G B dash E. Means already we know that when that at mid frequency this E is negligible. If you are when you are looking into this input side, this is a GM into VB dash E is acting as a open circuit, hence we can say that these two are in parallel. Therefore, we can say that the collector current IC, because this resistance is IC, if you want to find an IC, is equal to current flowing through this resistance RB dash E and current flowing through this and current flowing through this terminal. Because this RB dash C value is already specified at 1.3 milliamp 4 mega ohms, and this is about 80 kilo ohms. Hence, there is no current is to be flowing through that, minimum amount of current is to be flowing through that RB dash C. Hence, that current flowing through the RB dash C is negligibly small. Then we can say that IC is equal to GM into VB dash E, and also current flowing through this, where this VB dash E is this is also equal to that VB dash is nothing but a current flowing through, this is the means the voltage drop across that RB dash E. Then we can write that GM into IB, that base current, into RB dash E. Hence, we can say that RB dash E is equal to IC by GM into IB, where IC is equal to, from that low frequency analysis, that IC is nothing but HFE times IB divided by GM into IB. Therefore, this RB dash is nothing but a short circuited current gain of a H parameter divided by a trans conductance of an amplifier. Therefore, RB dash E is approximately equal to HFE by GM. That trans conductance GB dash E is defined as a reciprocal of the input resistance RB dash E. Therefore, this is equal to GM divided by HFE, where you are assuming that we are at a room temperature. The relation between the trans HIE, this resistance, and this resistance RB dash is given by HFE divided by GM. Next, if you consider the another important parameter is the feedback resistance RB dash at high frequencies. That a feedback conductance or a resistance is given by RB dash C, its conductance is given by this also equal to 1 B dash C. What is the value of this? If you want to define that a trans conductance, you have to set that input current 0 or a open circuit. When your input current is 0, then you are looking into this current is to be 0, then what is the voltage? That is HRE is equal to VCE. Therefore, we are going to get that HRE is equal to the input voltage is VBE and output voltage VCE. Therefore, the current flowing through this point is 0. Then that HRE is given by simply on V B dash E divided by VCE. Now, from this circuit analysis, means from the figure 2, we got this value, where because the voltage drop across HI is 0, therefore HRE is to be defined as VB dash E by VCE. Then what is the voltage drop across RB dash E? Then from this circuit analysis, this is also equal to, when you are looking into this, if this is to be driven by that VCE, then this VB dash E is given by means that is a voltage drop across RB dash E divided by the total resistance. This means you have to, this is to be driven by this VCE, then this is given by a VB is equal to RB dash voltage drop across this resistance divided by the total resistance RB dash E. Total resistance is RB dash E plus RB dash C. If you are manipulating this equation, you are going to get equating, you are going to get this is equal to RB dash E into VCE is equal to RB dash E plus RB dash C into VB dash E. If you take this ratio, then you are going to get that RB dash C is equal to HRE VB dash C divided by 1 minus HRE, where this HRE is negligibly small. Therefore, RB dash C is approximately equal to the HRE into, because we know that HRE value is to be 2.4 into 10 to the power of minus 4 2.4. Therefore, that RB dash is equal to HR into VB dash C, and this is also equal to the 1 by GB dash C. Now, we are found this value and we have found this value. Then what is this what is the RBB dash? RBB dash is nothing but a base spreading resistance. When you are applying KVL to this path, therefore you are going to get that RBB dash plus RB dash E. This, when you are comparing with respect to this, at this point this is equal to HIE. Already we know that this value RB dash is equal to 1 kilo ohm and RBB dash is 100 ohms. Therefore, this value is equal to HIE. We can say that RBB dash is equal to HIE minus RB dash E. Means that RBB dash values varies as the temperature is varies. This is also equal to approximately this RBB dash is given by this value, and then this from this value we can say that HIE is equal to that HFE times VT by IC magnitude. These are the means, from this we are finding that relation between this and this. Then what about this RCE? That RCE is nothing but a resistance lies in between the collector and a emitter. This can be obtained, means we have to find that output conductance. Output conductance is given by, that is GCE. This is also equal to 1 by RCE. If from this circuit analysis you are applying KCL at this mode, then that IC, applying KCL at this point, for example node, then IC is equal to current flowing through that RC is nothing but this is a VCE by RCE, and current is this constant current source, hence this is nothing but plus GM VB dash E plus current flowing through that RB dash C. This is nothing but on VCE divided by that RB dash C plus RB dash E. We know that this RB dash value is very large, therefore current flowing through is to be negligibly small. Then that IC is approximately equal to, if you are solving for the output conductance, then you are going to get, if you are simplifying this value, you are going, this is a one expression, and then if you are already, we know that HOE is nothing but a short collector current IC divided by VCE. From this circuit you are going to get, this is equal to 1 by RCE plus 1 by RB dash C plus RB dash E. Therefore, if you are comparing these two, your HOE is equal to, approximately equal to, because the reciprocal of RC is nothing but GCE, easy to analysis because this is a conductance, plus this is a conductances of this is given by GM into HRE. Therefore, we can got this if you are manipulating, simplifying this equation, if you solve for GCE, then this value GCE equal to, GC is equal to HOE minus a G B dash C into 1 plus HFE. This also, if you are further simplified, you are going to get HOE minus GM into HRE. This output conductance of a transistor are given by this expression. Finally, we conclude, means we are determined a various parameters, that is given, if you are table this, you are going to get a GM. Trans conductance of a transistor is given by, this is given by IC by VT, and the RB dash E input resistance is given by, this is nothing but a GM by HFE, and the base spreading resistance RB dash is equal to HIE minus RB dash E, and B dash C equal to R B dash E divided by HRE. This also we can say that in terms of a conductance, a G B dash C is equal to HRE into G B dash E. Finally, you are calculating that GCE is equal to HOE minus GM into HRE. If you are observing this relationship between the resistance RB dash E and RCE, all are depends on that a GM value. Means if you know the trans conductance of a transistor, we can able to determine the exact values of that on resistances at high frequencies, that is RBC, RB dash and RCE. Then if you observe here, this is to be GM is directly proportional to the collector current and inversely proportional to the temperature. If you are comparing these two with respect to the current and a voltage, a GM, a current increases, GM increases, a temperature decreases, GM is increases. If this GM is increases, then this RB dash E is also increases, and RBB dash means if this RB dash E is increases, this HI is constant, RBB dash is decreases. And then RB dash is nothing but RB dash E, it is directly proportional to GM. As the GM increases, RB dash C is also increases, and GCE is decreases because it is inversely proportional to the IE. And other two parameters at high frequencies are a CC and CE. CE is an independent of a transistor because that is a resistance between the base and a collector, and CC is depends on the collector current. Therefore, if the IC is increases, a CC is also increases. These are the various parameters we have studied from this transistor characteristics, and then we drawn the equivalent circuit, and also we found that relationship between the high frequency parameters and a low frequency parameters. Okay. For this case, we have derived so many parameters, means we have to finding that relationship at high frequency and low frequency. Now, what is the current gain? Because we are shown current gain is decreases at high frequencies. What is the current gain of a transistor or a voltage gain of a transistor at high frequencies? For this case, for example, if you consider the hybrid pi circuit at low frequencies, equivalent mode, because we are neglecting that a CE and CC. And if the load resistance is RL is equal to, you have to take the conductance, a reciprocal of that conductance, then you have to prove that VC is equal, K is equal to VC by VB dash E minus GM plus GB dash C divided by GB dash C plus GC plus GL. Then how do you solve this? Now question is, you have to find that relation. We are applying KCL at okay. For this we have to find applying KCL at this point. Applying KCL at this point, you are going to get that we know that voltage at this, current at this is to be given by nodal analysis, then VCE by RCE in a single line, plus that current flowing through this is nothing but GM into VB dash E, plus that current flowing through this branch is G VCE minus VB dash E divided by R B dash C, plus if you connect a load resistance RL, then that current flowing through that is given by VCE by RL, this is equal to 0. If you solve this problem as it is, you derive an expression, then because of this a parallel combination, this that relationship is to, that analysis is to be too complex. To reduce the complexity, you have to convert that resistances into the conductances, then this expression is becomes a G CE into VCE plus a GM into VB dash E plus VCE minus VB dash E into G B dash C plus VCE into GL equal to 0. If you are solving this equation further, we are going to get to take all VCE into one side. VCE is equal to, if you take this is equal to GCE plus this is GB dash C plus GL equal to minus GM plus this is to be a GB dash C into VB dash E. If you take this ratio, then you are going to get the value of that K is equal to VCE by VB dash E minus GM plus GB dash C divided by GB dash C plus GCE plus GL. Next question is, what is the voltage gain between, if you are applying and some input voltage VI is applied at this point, then what is the relation between that output voltage and input voltage, where that VC is equal to V0 and input voltage is applied is VI. Then what is the relation, that voltage is nothing but the voltage gain of a transistor. That voltage gain of a transistor means already we know that ratio VCE by VB dash E. Now we need to find that what is, we have to write AV, that derivation, instead of deriving from the beginning, we can start with AV is equal to a VCE by VI. This can, there is no direct relation, then this can be defined as a VCE by VB dash E into VB dash E divided by VI. This is nothing but a K into that value VB dash E divided by VI. Okay. For this case, we have to find that that ratio between this value. Then how do you found this? Next, we need to apply that. When you are applying KCL to this path, then you are going to get applying KVL to this path, because voltage drop across this RB dash is nothing but VB dash E. Therefore, you are going to get this VI. Once again you are applying KVL at this point, you are going to get VB dash E minus VI divided by RB dash plus VB dash E by RB dash RB dash E plus RB dash E. We can, from this we can say that equation VB dash E minus VI by RBB dash plus VB dash E by RB dash E plus VB dash E minus VCE by RB dash C is equal to 0. Therefore, from this you have to solve for VBE dash. VBE dash is equal to, you can say that this is can be defined as RBB dash is nothing but GBB dash plus GB dash E plus GB dash C minus VI into GBB dash plus this is equal to VCE into RB dash, sorry, GB dash C. From the value of K, if you substitute VC is equal, VB dash E equal to, that is equal to, from that previous case, that is VB dash E by VCE, this is equal to K, this is given by minus GM plus GB dash C divided by GB dash C plus GCE plus GL, where these are the conductors. If you substituting into this VB dash E, then you are going to get GB dash C plus GCE plus GL into GBB dash plus GB dash E plus GB dash E into VCE divided by minus GM plus GB dash C minus Vi GB dash equal to VCE GB dash C. If you take this value into this side, then this is equal to, if you take VCE is common, then LCM, then you are going to get GB dash C plus GCE plus GL into GB dash plus GB dash E plus GB dash C minus GB dash C into minus GM plus GB dash C is equal to Vi by GBB dash. The voltage gain of the amplifier for at the transistors at high frequencies are given by VCE by Vi. This is going to cross multiply, you are going to get GBB dash into minus GM plus GB dash C divided by GB dash C plus GCE plus GL into GBB dash plus GB dash E plus GB dash C minus GB dash C into minus GM plus GB dash C. The exact expression for the voltage gain at low frequencies are given by this expression. We know that already RB dash C is higher, therefore its conductance is very poor, therefore that resistance is to be negligible, that conductance is poor means this value is negligibly small, and then this term is vanishes, then this term is also vanishes, therefore you are going to get minus GM into GB dash BB dash divided by GCE plus GL into GBB dash plus GB dash E. If that GC once again this is about 80 kilo ohms, therefore reciprocal of GC is equal to 1 by RC. This is about 80 kilo ohms. When this is if this RL is much smaller than that RC, then this is approximately equal to once again a minus GM plus into minus GM into GBB dash divided by that GL plus GBB dash plus GB dash E. This is an approximate voltage gain of an amplifier of this circuit as shown in this figure is given by this value. Okay. For this case we got this AV, but we need to calculate the current gain of at the high frequencies. We need to study a short circuit current gain. In the present class we have discussed the Darlington emitter follower of a transistor amplifier at low frequencies, and also we studied a definitions and of a transistors at high frequencies and a relationship between a pi model and hybrid model at low frequencies, and also we have derived an expression for the voltage gain of the amplifier AV, and also we defined. This can be further simplified by using a Miller's theorem. We will discuss in the next sessions. Thank you.